Thanks, Christina, for the invitation. Yeah, so I started looking at harmonic maps into metric spaces with upper curvature bounds a few years ago, and I'd like to talk about sort of some of the results in that area from a particular perspective that I know pretty well. I'll mention some other perspectives when I can, if I have time. And I'm going to talk about two applications, and one of these applications I know much better than the other. So that one I'm going to talk about first. The other one I've just started studying, sort of trying to understand what one can do with harmonic maps in the second setting. And so because we're going to be talking about harmonic maps into metric spaces, I'm only briefly going to remind us what they are in the smooth setting. And I think for this audience, I should be okay to not say much else. So of course, if you have Riemannian manifolds, you have a map between them, then the map is called harmonic if it's a critical point for the energy functional, which is given here up to a 1/2, depending on your preference. And so we're going to try and make sense of energy and harmonicity when we don't have smoothness and we don't actually have a differential. And in the smooth setting, there's these sort of natural subsets one has. So you can look in either direction you want to look. Sort of the weakest notion is the weak notion of being harmonic. So you can't actually satisfy the Euler-Lagrange equation pointwise, but you can satisfy weakly. Stationary, of course, are critical also with respect to domain variations. And this lets you determine tangent maps, the existence of tangent maps, which actually is really important for any kind of results in regularity and understanding like the structure of the singular set. And then local minimizers will be of course, it's minimizes the energy on small balls, on sufficiently small balls. And then the global minimizer would be, of course, if you minimize energy compared to any other map from M to N. And obviously, they show up everywhere. Some quick reminders: harmonic functions, geodesics, isometries, totally geodesic maps. Minimal surfaces are conformal harmonic maps, and we'll see those appear a few times. And then holomorphic maps between Kähler manifolds. We'll also talk in the second application about totally geodesic maps, which are maps that take geodesics to geodesics, right? So you're interested in understanding they have much more structure than just a sort of standard map. Okay, and then the global existence results I'll mention are here only because I picked these two only because these two will appear in the singular setting also. So there are obviously almost infinitely many harmonic map results in the smooth setting that are all quite lovely, but these two will show up again in our setting. So Eels and Sampson in the 60s gave the first existence result for harmonic maps between compact Riemannian manifolds. And the only condition was that the target had non-positive curvature. And the reason for this condition, we'll see later, gave regularity of these maps. So they looked at a parabolic problem and showed that you could take t to infinity, and in the limit, you'd find a harmonic map. Sachs and Uhlenbeck, 20 years later, it took before there was this result where the target was not necessarily non-positively curved. So you have a target with potential points of positive curvature. Now you're only mapping from Riemann surfaces. So you take a compact Riemann surface to a compact Riemannian manifold, and they showed the existence of harmonic maps in a sort of a dichotomy. And this result I'll talk about a little more in the metric space context later, so I won't say too much about it now, except to say that if your domain is a sphere, then you get a harmonic map from a sphere, which of course is then necessarily conformal almost everywhere, and then minimal. So they get minimal two spheres, but you can't guarantee for sort of an arbitrary compact Riemann surface that you have a map from there that's harmonic. Okay, so how are we going? I should first say, what space are we going to work in, and then how do we talk about how do we describe energy and harmonicity there? So we're going to be dealing with cat kappa spaces and what are locally cat kappa spaces. And so I'll only care about when kappa is 0 or positive. So I'll give the description of those two. So we'll start with a complete geodesic space, and we'll say it's cat 0 if every geodesic triangle in the metric space is no thicker than a comparison triangle, geodesic triangle, in what we call the model space in R2. So the 0 comes because the model space has 0 sectional curvature. And a picture of that I almost hesitate to do, because I always make it either look equilateral, or I can't get the sides right. So we'll see if I can try and do a picture here. So here's your PQR, and then in the model space, of course, the sides are straight lines. Almost did a good job here. So these are supposed to be the same side lengths. And then what we mean by this no thicker than, thinner than is easier to say, but not as precise, is that if you take any 2 points on sides, opposite sides, and you look at the length here, so this L, so call this X and call this Y, and you can determine sort of comparable points on your other triangle by putting them in the same distance from Q prime. So here would be X prime, and here would be Y prime, something like that. And here's your sort of L prime. That's supposed to be a geodesic. Then L should be less than or equal to L prime. So it's sort of relating. It's a relationship between the spreading of these geodesics. Okay, so this is for 0. And then when we look at cat kappa, when kappa is greater than 0, the only difference is that your geodesic triangle in your metric space has to be sufficiently small, and the comparison is now the model space is now a sphere with sectional curvature equal to kappa. So the radius 1 over root kappa. So then what does sufficiently small mean? Is just to preserve geodesic convexity. So you just want to have it so that you don't end up passing through a hemisphere. And then often I will talk about locally cat kappa. And locally cat kappa just means that every point in your space has a neighborhood that's cat kappa. Okay, so that's all we mean. So really, locally cat kappa is trying to characterize the fact that this property is we're interested in is really a local property. It's if we think about curvature, this is a local thing. And then one other thing I'll say is that locally cat 0 we'll often see is NPC. So if you see NPC non-positively curved because it's the curvature condition there, they're the same thing. Okay. Okay, so some examples, not surprisingly, manifolds with sectional curvature bounded above by kappa. That's what you're trying to model. So that's sort of an easy example. Surfaces with metric lambda dz squared, norm dz squared, which the metric could be possibly degenerate. That's the point. And if they satisfy this differential inequality, then they actually have curvature bounded above by kappa. And let me say throughout the talk, anytime I write an inequality, I'm meaning it in the weak sense. So I'm not going to write it in the weak sense, but I'm meaning it in that sense. Euclidean buildings and spherical buildings are locally cat 0 and cat 1 respectively, and they're sort of special examples because they're simplicial complexes, and the top face in the Euclidean case is smooth and flat, but where the simplices come together, you could actually have infinite negative curvature concentration. So, and you're not a manifold, you're not smooth at where these come together. So you lose your manifold structure, and you don't have a lower curvature bound in many cases because of the simplex structure. Spherical buildings, you have curvature 1 on the top face. And then the Weil-Petersen completion of Teichmuller space actually is a non-positively curved space, which one of my collaborators has a rigidity result there using this fact that she can look at it as an NPC metric space. And I'll mention the result briefly if I have time. So these are some examples. So we want to talk about harmonicity. We need a notion of energy. So we want to talk about what a Sobolev space might look like and what energy might be. And I'm going to use the definition Korevaar and Schoen defined in 1993. There are, as I said, there are other notions for Sobolev spaces and energy. Reshetniak has one, and there's a Newtonian Sobolev space, which I think is more closely related, or what if one wants to look at it in terms of modulus of curves. The reason I like this one is that you can use this definition to get differential inequalities that look quite similar to differential inequalities you get in the smooth setting. And so you can sort of, there's a lot of analogous work one can do there, and you'll see some of those things. So we're going to start with a map from we're always going to be dealing with a Riemannian manifold as the domain. So a Riemannian manifold to some complete metric space. And if the map is in L2, which just means the squared distance from a fixed point has finite integral, is in L2, then we're going to set this sort of epsilon energy density, we'll call it, as almost the average of the squared distortion of U over the boundary of a ball. So, so you have the sphere of radius epsilon centered at x. You take the squared difference quotient between U of x and all of the image points on the sphere. And then this is just the measure of the sphere of radius epsilon centered at x. So it's almost the average. The only difference is this is the ball volume and not the sphere volume, but that is just coming in because later we want to have in the smooth setting, if this is a map to the reals, we want it to agree with what you'd get if it were a map to the reals. So don't get hung up on that. So they define the energy of U by taking these epsilon energy densities and looking at them as linear functionals here. They're acting on these phis by integration, and these phis are the sort of natural, the compactly supported feed between 0 and 1. We're going to look at the soup of the limb soup as epsilon goes to 0. And if the energy is finite, so if this is the notion, if the energy is finite, then they say U is in W12. And if the energy is finite, then you have these bounded linear functionals. And so Riesz representation tells us that they actually converge to a measure weakly. So there's some measure that these are going to converge to if the energy is finite. We could call it like dE. And then they're able to show that measure is absolutely continuous with respect to Lebesgue measure. And so not only do these measures converge weakly to a measure, but they converge weakly to a measure that can be written as a function dx. Okay, and so that function is what we'll call the energy density function of U. One thing I'll say about this notion of energy is they actually, they have to show that as epsilon goes to 0, somehow you're getting better and better approximations. You have kind of a monotonicity as epsilon goes to 0. They can't quite get that, but they get that it's monotone enough. But what I mean by monotonicity is if you imagine you're trying to approximate a length of a curve by partitioning in geodesics, and you want to keep doing, as you refine, you should get closer to the length. That should be you should be increasing, right, in the length. So this monotonicity doesn't quite hold in the same way here, but they are able to get something good enough that they can that we have something well defined and we get good convergence. Okay. So the notion we're going to take is a map U is going to be called harmonic if it's locally energy minimizing. Okay, and what we mean by that is if we compare, so for every point x and m, there exists some r greater than 0, so that if the distance between U and V is in, so sorry, I should say has trace 0. I'll just write this, has trace 0 on BRX, then the energy of U restricted to BRX is less than or equal to the energy of V restricted to the same. Sorry, that was a little heavy-handed. I probably didn't need to write all of that, but that's what we mean by local energy minimizing. Okay, so locally energy minimizing means we can do domain variations and target variations. And with respect to both, we should always have the energy of U on that where we're doing the variation should be less than or equal to the energy of the variation. And that gives us a lot of things. So here are the comparable global existence results. So in 93, in this same paper, Korevaar and Schoen generalized the Eales and Sampson result to metric spaces with, oh, did I say cat 0? I was supposed to change that. That's NPC universal cover. But oh yeah, but it's okay, it should be fine. But with NPC universal cover. And their approach is really a variational approach. So thinking of it as a calculus of variation, as a variational problem. Energy as a variational solution, or harmonic maps that way. And they establish existence of Dirichlet solutions, and regularity. The best regularity you can get is Lipschitz, of course, but they get the Lipschitz regularity, and then they have to sort of build up this equivariant map, find a minimizing equivariant map in a sequence, or take a sequence of equivariant maps with the energy decreasing and find a minimizer, and then establish that that's actually harmonic. So this is the sort of the game they're playing there. With a number of collaborators in a paper that came out in 2020, we generalized the Saxon-Uhlenbeck result. So the targets now have are locally cat-kappa spaces. And so we show the existence of minimal two spheres and this dichotomy that I'll show more precisely on another slide. Okay, that's all I'll say about those at the moment. Let's see the time. Okay. So the first application I want to talk about is a uniformization application. And I want to relate it to the measurable Riemann mapping theorem, in part because I think it has so many parallels in many ways, although it's not quite as general as this. So there are many forms I think you can see the measurable Riemann mapping theorem in, and I'm going to put it in the form that's the closest to what I'll be talking about. So you have some mu from oh, this is supposed to have, just in case, it is just L infinity. So mu from C hat to C hat. It's an L infinity function with the L infinity norm bounded above by 1. Then the result is there exists a unique, and of course this is up to Mobius transformation. There exists a unique F that's a homeomorphism from the sphere to itself, so that the Z bar derivative of F is equal to mu times the Z derivative of F. If you're interested in Teichmuller theory, this is something you would know a great deal about. If you've never looked at Teichmuller theory, you might not have seen this result. I see it now everywhere as I look at anything related to the Teichmuller map. But this is a result that what I like about it in particular is this you can see is in some ways an analytic, really an analytic measure of distortion in a way. Right? Because if mu is 0, of course you have a holomorphic map. Okay. And as mu gets closer to 1, you're getting very far from this. And how this plays out geometrically, the thing I like is that it's very clear what the geometric interpretation is. Again, if you know the Teichmuller theory, this is not new for you. But you can read off the dilatation of F at every point by looking at this ratio, 1 plus the norm of mu divided by 1 minus the norm of mu at Z. And the dilatation is really just the eccentricity, so of the ellipse that you're mapping to. So if you take infinitesimal circles, what do they map to? Say this is Z, and this is F of Z. When you look at what's happening as that radius goes to 0 of the circle, you get some infinitesimal ellipse, and the ratio of these two sides is going to be that H. So that's really the eccentricity, reading off the eccentricity of an ellipse there. And the nice thing about this from our perspective is that, of course, this one can measure this kind of thing very easily, even for maps into a metric space. You don't need to be able to take derivatives to understand this interpretation. So this is, in some ways, this is more of a geometric measure. distortion. And when you are in the metric space setting, if you have a homeomorphism, it's quite straightforward to talk about what this H is. Really, the H is just, you take, because it's a homeomorphism, you just take the max of the distance from the image center, and then you divide by the min of the distance from the image center. And even if you don't have a homeomorphism, you can still cook up a relation with imps, sups, and inequalities. It's not so hard. In that setting, and in this setting as well, we're going to define just this H as, the sup of overall Z of H of Z, and we'll say that F is H quasi-conformal. So if F is one quasi-conformal, in this case, then you get a, sorry, I lost track of myself. Sorry. Oh, right. If F is one quasi-conformal, then mu is 0, right? And you get an almost conformal harmonic map. So one quasi-conformal is almost conformal. Okay. So the question that we were trying to answer was in some ways similar to this, and we are not the first. I'll point out other results as well. But if you have a metric space that's homeomorphic to the two-sphere, the question is, what conditions could you put on its metric that would give you a homeomorphism that has some kind of controlled distortion? So is either quasi-conformal, or most of the results actually are about quasi-symmetry, which is a different kind of measure of distortion, which gives you control on distortion kind of at all scales, whereas quasi-conformal gives you control on distortion at infinitesimal scales. This is coming from a famous conjecture in geometric group theory, which is sort of, you have a hyperbolic group and the boundary at infinity is homeomorphic to the two-sphere, and you want to try and understand if it's quasi-symmetric to the two-sphere. So if you have that kind of distortion, the control on the distortion. So there are sort of four collections of work that I'll mention very briefly. And Reshetniak didn't look at this question to the two-sphere, but Reshetniak was probably the first one, as to my knowledge, who thought about uniformization for metric spaces at all. So he probably started the business, as far as I know. To this particular question, Bonk and Kleiner gave the first really excellent result, which says that that if the metric space is Alfers2 regular, which essentially is telling you about the Hausdorff measure of balls of radius r is comparable to Euclidean balls, the measure of Euclidean balls, and locally linearly contractible, then you actually have a quasi-symmetric map. So they recognized that you have to have, as soon as you're quasi-symmetric, you have to also be locally linearly contractible. And so really they just said you have to add the Alfers condition. So you have to add this kind of Hausdorff condition on control on balls of radius r. And then there was a long gap before I think there were results that were looking back at this problem. And my only thought is that the timing, it was 02 and then Perelman came, and because this is all related to Thurston's geometrization. So I'm not sure why there was such a big gap, but that's why perhaps there were people weren't looking at it as much anymore, or maybe it's just hard. So Rajala in 2017 and Letrek-Wenger in 2020 had results that at the end of it, they could remove part of the hypothesis from Bonk and Kleiner. They could remove the lower bound on the Hausdorff control of these balls, and they got quasi-symmetry. And there's sort of different conditions they put on their metrics. I'll point out that the Letrek-Wenger result is probably in some ways the closest to the result that I'll mention that I did with Cicamesi, because they use a harmonic maps approach. So they look at solving the Dirichlet problem locally and building up from there to find sort of a quasi-conformal structure. So what I did with Cicamesi, came out last year, is that if you put the cat kappa condition on on your metric space. So you know you're homeomorphic to the two-sphere and locally cat kappa. Then there's a map that's an almost conformal harmonic homeomorphism, and it and its inverse are one quasi-conformal in the metric space sense. And of course, you expect uniqueness up to Mobius transformation, and we get that. One thing I should say is what can we possibly mean by almost conformal in this case? And this goes back to the Korevaar-Schoen definition of energy, because Korevaar and Schoen define not only energies, but they define directional energy densities. Not only the energy densities, but directional energy densities. They can give a notion of an inner product. So they of a pullback inner product structure. So if they have this sort of, this is the notation, this is the directional energy density in the direction V, then you can cook up this inner product structure by taking a quarter of U star V plus W squared. You know, they show you have for these this relation, you get all the things you expect to get. I mean, really, you start off by showing you have parallelogram identities are satisfied and this kind of thing. And so they have this inner product structure. And then almost conformal means that if V and W are both del X, the X direction, and then V and W are both the Y direction, that those are equal. The pi's of those are equal. And then if V is del X and W is del Y, then you get 0. And so you have the ability to talk about sort of conformality in this case, which is, I guess, in a way, it's not surprising. It should be telling you that infinitesimal circles are going to infinitesimal circles, which is what the one quasi-conformal is telling you. But making sense of those two things separately, one in the sort of analytic direction and one in the metric space direction. And we show that they do in fact agree. So we use harmonic maps to get here. The cat kappa condition we used because we had this global existence result, and we were kind of curious why we couldn't get anything better with this global existence result. So we came at it by saying you have this harmonic map to the two-sphere. Once you have this harmonic map, can you improve something? Can you change it, modify it in some way, and make it a homeomorphism? So let me point out the global existence result. This is really what Sachs and Uhlenbeck have. So Sachs and Uhlenbeck say you replace locally cat kappa just by a Riemannian manifold, compact Riemannian manifold. So you take a compact Riemann surface, you map to a compact locally cat kappa space. If you have a finite energy continuous map between these spaces, so C0 intersect W12 is not empty, then you have this dichotomy. Either there's a harmonic map homotopic to this phi, or there's an almost conformal harmonic map to the two-sphere. And of course, if sigma is the two-sphere, then this tells you that you have a harmonic map to the two-sphere, or from the two-sphere, right? Because in either case, you have this map. But the problem, you can't get uniformization because, and this is the same thing that happened with Sachs-Uhlenbeck, in this dichotomy, even if phi is a homeomorphism, of course, U is degree 1, but you don't know if it's a homeomorphism, but probably it should be somehow something you think it should be a homeomorphism. But maybe you don't get the U, maybe you get the other bullet point. And then the other bullet point, V is almost surely doesn't have degree 1. And in fact, actually with Sajjad Laxton, who's here, we proved the full bubble tree picture for these maps, from compact Riemann surfaces to locally cat kappa spaces. And so you can keep track, you can keep better track than in this particular, than we did here. And you could say for a sphere, you could keep track and see that you had sort of a sphere map and another sphere map. And they should, you would connect some of these two maps and in total their degree is 1, right? But you don't expect them, neither of them is degree 1. So we wanted to see if we could improve this to a homeomorphism. And the way we did that is we showed that in either case, this harmonic map you get actually has to be a branched cover. And then once you have a branched cover, you can factor through where you take, any 2 points that map to the same point. In S, you just factor through, you make them equivalent and factor through and show that, that in this projection you've done, that projection actually gives you the Riemann sphere. And so you now have a map from the Riemann sphere that's a homeomorphism. And you establish its harmonic because it's related so clearly to the map U. It's sort of like we look at a fundamental domain, is what you could kind of imagine. So how do we do that? I'll just briefly say the kind of the statement of the theorem. So, if you have a harmonic map from a Riemann surface to a locally cat kappa space, we'll just say it's non-degenerate. We're trying to generalize the notion of a full rank differential. So if infinitesimal circles don't collapse, they always map to infinitesimal ellipses. And any tangent map of U, we make it precise with tangent maps. Any tangent map of U doesn't collapse along a ray. And then the theorem we prove is that if you have a proper non-degenerate harmonic map from a Riemann surface to a locally cat kappa surface, then you actually have a branched cover. And so to do this, we show the maps are discrete and open. And so you get local homeomorphism away from some possibly quite bad set. It has topological dimension 0. And then we use the structure of the harmonic maps and the order function to show that the set of branch points is actually discrete. So the point here is that any harmonic map from the 2 sphere is non-degenerate because any conformal map has to be non-degenerate. You can't have this collapse. Any almost conformal map, you can't have this collapse. And so then we can apply this branched cover result to our global existence result. So now in the time left, I'm going to kind of completely switch directions and mention a little bit about another area, another application. And again, there are people in this audience who probably know these results, some of these results much better than me, but I find it interesting and important, and I've been trying to learn about them and how to use them. Just a reminder and sort of classically, the easiest sort of rigidity theorem to state, classically, what are we interested in? Mostow's rigidity theorem from 1968, I think, is probably the easiest one to state. So you have 2 compact hyperbolic manifolds of dimension greater than or equal to 3. And if there's an isomorphism between their fundamental groups, then actually the manifolds are isometric. And
correction. Most we haven't formulated the theorem.
Sorry, I just can't hear so well.
I think this theorem is due to Margulis.
Oh, this one's due to Margulis?
In this form, yeah.
In this form. Oh, I apologize. Okay, thank you.
Homeomorphic or something, yeah.
Okay. Thank you. Okay, I apologize. I think I saw it in this form, but you're right. I think it was stated later. Yeah. Okay. So Margulis. This should be Margulis. Okay. Okay. Thank you. And of course, then it's probably 68. Okay. So the idea is somehow if you have these groups, well, I guess I'll just go to the next slide. What is the sort of basic principle of rigidity? Is if you have, I'll state it in the case where gamma is pi 1. So you have some complete Riemannian manifold. You have its fundamental group. M tilde will, of course, denote the universal cover, and X will be a metric space for us. Then if you have some representation, which is just a homomorphism between pi 1 of M and the isometry group on X, then you try to understand if you have a harmonic map that's equivariant with respect to this gamma, by which we mean exactly this, U of gamma acting on X is rho of gamma acting on U of X, then if this map is harmonic, what can you say? What else can you say about it? Is the map constant? Is it an isometry? Is it totally geodesic? And this, the hope is that once you say something about, if you can say something about U, you can say something about rho, right? So that's sort of the idea. And again, if you look back, it's really, you're trying to understand, you have some homomorphism between groups that are acting on these two, well, usually manifolds, but now manifold and metric space. What can you say about these, the manifold in relation to the metric space? So this is not the first result that was done here, but I think it's interesting to state first because it doesn't use what everybody else uses. So it's very unique to the particular setting. So you start with the flat torus. You have a map from pi 1 of the flat torus to the isometry group of a cat 0 space. And then any gamma equivariant harmonic map, from Rn, yes, this should be from Rn, the universal cover, from Rn to X is totally geodesic and flat. Okay, and so by flat here, we mean that the pi ij is equal to delta ij. So the pullback inner product structure is a flat structure. And this, I'll remind us of Bochner's formula on the next slide. Surprisingly, this doesn't use Bochner's formula. It just uses their definition of energy and these sort of mollifications of the energy. You can think of them as you take the energy and then you look at the sort of center of mass of the map and you compare the energy to the original one. And it uses the flatness because of the domain, because that gives you fewer error terms, and then you can actually sort of write down explicitly what the new energy is. And then, in the only way you could kind of hope to do this, you have the string of inequalities, and at the end you get the energy of U again, which tells you everything was an equality, and that's how you showed the total geodesicity. So it's sort of, this is the game that they can play. But everything else that I've seen in this setting has to use the Bochner formula in some way. And so there's sort of two things that have been happening. So just a reminder of what the Bochner formula is in the smooth setting. And, if you don't deal with it a lot, just look at this part. This is the important part. If Ricci on M is greater than or equal to K, and the sectional on N is less than or equal to kappa, those are hard to write differently, okay, then you get this inequality I've highlighted. And what you see here, what you notice is that if K and kappa are both 0 and M is closed, then you can use the divergence theorem to show that U is totally geodesic, right? If I should have written closed, sorry. If M is closed and big K and little k are 0, then this integrates to something greater than or equal to 0, but this integrates to something that equals 0. And so grad du is equal to 0, and that tells you the map's totally geodesic. This is the vanishing of the second fundamental form. So there's sort of two ways the game is played at this point. And I think probably these are the only two ways. You either, in the setting we're dealing with, where you're mapping M to a metric space, you either try and show enough regularity of your maps so that on large sets, they're maps to really manifolds, and you can appeal to the standard Bochner formula on large sets, or you try and find a Bochner formula for the metric space. So for metric space targets. So both have been used, both have been done, but I just want to point out there's kind of two ways. The second thing has only happened quite recently. Actually, not completely, but sort of a full story has only developed in the last year, I think, last 2 years. By the way, the Eels and Sampson, of course, they use this kappa being greater than or equal to 0 to make this term go away. And so they get this sort of almost subharmonicity of the energy density function. You can get regularity from this. So that's how the regularity, this Bochner formula plays a major role in regularity theory as well as rigidity. Okay, so the first result that was proven and was by Gromov and Schoen in '92, and it was to answer a question of a rigidity question. So it was the non-Archimedean superrigidity. So essentially there were a few cases still remaining with respect to rank 1 symmetric spaces. And they answered the question. They showed that in these rank 1 symmetric spaces that weren't the real or complex hyperbolic, where there's counterexamples, if you're mapping to Euclidean building, you get a totally geodesic harmonic map. Okay, so you can correct me if you want to make a comment, Misha. I saw your light turn green, your tile turn green, that's why. So how does this sort of work? So where does the p-adic thing come in? Well, p-adic groups act on these Euclidean buildings by isometries. So you get the isometries of X appearing in your representation because of the p-adic groups acting on them. And Euclidean buildings are these special examples of not NPC spaces, as I pointed out. And the game here was that they actually showed that these maps were regular enough to invoke the Bochner formula on very large open sets. And so they could get this total geodesicity from that direction. After that, so what Korevaar and Schoen had set out to do, I think, was to try and generalize this sort of idea so that you didn't have to have a Euclidean building as your target. And it wasn't, to my knowledge, they didn't sort of complete their full program, but they did establish along the way. Oh shoot, I forgot I put this one in too, but I'll come back. They did establish on the way a sort of weak version of a Bochner formula into Cat0 or NPC spaces to give them the Lipschitz regularity of the harmonic maps. So they are sort of starting this process of trying to find non-smooth Bochner formulas. Okay, sorry, I forgot I put these in because these are some other results that are of the same type as that Gromov-Schoen one in the strategy, that they take these harmonic maps and they look at the singular set, and they show the singular set is small enough that you can appeal to a Bochner formula, a smooth Bochner formula on a large enough set. And so the first one is they generalize this Gromov-Schoen result to hyperbolic buildings. So instead of Euclidean buildings, you're mapping to hyperbolic buildings. And one key aspect of this proof that's quite different is that, you know, there's this splitting at points of order 1, and in the Gromov-Schoen result, you can split the map into some Euclidean space and then some complex of lower dimension. And the map into the Euclidean space is regular, and it's a harmonic map, and the map into the space of the complex of lower dimension actually is where all the singularities would have to lie if you were at a singular point of order 1. And in the Gromov-Schoen case, both of the maps are harmonic. So Daskalopoulos and Messi look at the same idea of trying to take a map and take sort of a Euclidean part and a non-Euclidean part, or the analogy, sort of analogous thing, but the maps are no longer both harmonic. And so that makes the game much harder in that setting. And then very recently, they showed that the mapping class group in some cases can uniquely determine Teichmuller space as a complex manifold. And this is, they're using the fact that I mentioned earlier that the Weil-Petersen completion of Teichmuller space is non-positively curved. So if you put that metric on Teichmuller space, you get an incomplete metric. When you complete it, it's no longer a smooth manifold. It actually becomes just a metric space. So there was that dichotomy. There's the people showing regularity, and then there's an attempt to get Bochner formulas. And I just mention a few to show sort of where we are. So Messi gave a result where the domain is a flat disk and the target is cat kappa, and she actually proved that Laplace log lambda inequality I mentioned at the beginning for minimal surfaces, and showed that this gives curvature bounds for minimal, so for conformal harmonic maps. And then Friedan and Friedan-Zhang very recently were able to get a Bochner formula where they had a Ricci term in that formula as well. But I think I'm only going to show the kind of most complete one that was proven in 2019, which is that if you have Ricci bounded below by K, X has curvature bounded above by kappa, and you're looking at the Lipschitz map, then you get something that looks quite like, in fact, you know, if you're looking at the inequality thing, it looks almost identical to what you see in the smooth setting. And so this could give you, at least when M is closed, you get that for K and kappa 0, you get that your map has constant Lipschitz function. So the sort of maximum stretch at every point is equal. And this has gone even further in the last 2 years as well, as now there is a notion of a harmonic map from an RCD space to a Cat0 space. And there are now this year on the archive in the last 2 months. And so this is where I saw these posted, and I thought, oh my goodness, I'm trying to understand what they're doing here, and I'm learning a lot about RCD spaces as I go. But if you have an RCD-KN domain and an NPC target, then these are actually distributional. Then you can show these two inequalities that look somewhat like the Bochner one. So Gillies doesn't have a Hessian term, and the Mondino-Samola one has a Hessian term, but Gillies also has this du, like what is the differential here? So this is not the sort of analog of the Cheeger energy, the df of, or the du that shows up in the Cheeger energy. It's trying to take that and improve it so that you can think of somehow, even though you don't have tangent spaces and cotangent spaces on your RCD space, Gillies cooks up this notion of like the cotangent module. So he's thinking about sort of the bundle and not at every slice having a vector space necessarily, but a module. And he, from there, he gets this notion of the differential. So in some ways, Gillies, it doesn't have a Hessian term, but it has the sort of closest parallel to the differential in a way. And again, these came out, I think, really very recently, maybe February, March. And then maybe even a month or two later for one and the other. But this is where things have been going in terms of rigidity. And I think it was the initial reason people started looking at harmonic maps to metric spaces, and I think it's proven quite fruitful. So I think I'll just stop there. I think I'm exactly on time. Okay, I'm exactly on time, so I'll stop there.